This experiment is on measuring temperature coefficient of resistance of copper and the energy band gap of silicon. On this aluminum rod, there is a hole in which we have put a copper coil SW42 gauge with a resistance of the order of 25 ohms. On the other side, there is a hole in which a PT100 platinum thermometer is placed. A silicon 1N4148 diode is pasted on this face with araldite. All the leads come to the terminal block. The two blue banana plugs are connected to the platinum 100 resistor. The two green banana plugs are connected to the copper coil. The silicon diode is connected between the red and black terminal here. The red is positive, black is negative. So, the forward direction is from red to black. Between the red terminal and this yellow terminal, there is a 2-point K resistance connected at room temperature. And between the black and the yellow, there is a 470 K resistor connected at room temperature. All the connections are marked here. The 2K, the diode 470K, platinum 100, copper coil. Terminal numbers are also marked 1, 2, 3, 4, 5, 6, 7, 8. I will now put this insert into the furnace of temperature coefficient of resistance of copper is a very easy experiment. The resistance of copper varies with temperature. In a narrow range of temperatures of about 100 degrees, the resistance varies as RT is R0 into 1 plus alpha T, where R0 is the resistance at 0 degrees centigrade and T is the temperature in centigrade and alpha is the temperature coefficient of resistance. If we pass a constant current of about 5 milliamp through a coil of copper of resistance about 25 ohms at room temperature, the potential difference across the coil in millivolts will be proportional to the resistance. We measure this voltage at different temperatures T. A plot of the voltage is made against temperature and fitted to a straight line. The intercept V0 is proportional to R at 0 degree centigrade and the slope is proportional to R naught into alpha. So, the temperature coefficient of resistance alpha is found by dividing the slope by the intercept. This is the principle of the experiment. We use a silicon diode to measure the band gap of silicon. The forward current I of a silicon diode as a function of the forward voltage at a temperature T in Kelvin is given by I for the voltage V is the reverse saturation current I reverse, which is a function of temperature, and this is the I reverse value at temperature T into exponential the electronic charge, the voltage, forward voltage you apply, divided by K, the Boltzmann's constant, T, the temperature in absolute, and a factor eta called the non-ideality factor. This has a value close to 2, 1.8 to 2. So, if we plot logarithm of the forward current as a function of the forward voltage, the slope beta is given by 1 by eta into k by e into capital T. So, we can find the non-ideality factor from the slope beta, temperature of the silicon diode in Kelvin, and the value of k by e, Boltzmann's constant, to electronic charge, which is 86.6 microvolt per Kelvin. This is how we find the non-ideality factor. Then, to find the band gap, we measure the reverse saturation current as a function of temperature. The reverse saturation current is found by applying a large voltage, 9 volts, in the reverse direction. The reverse saturation current varies with temperature as I reverse T, some constant I naught, absolute temperature power 3 by 2 into exponential minus the band gap divided by non-ideality factor k by e and absolute temperature T. So, if we measure I reverse as a function of T and take natural logarithm of I reverse minus 1.5 log of the absolute temperature, that will be equal to log I naught, which is a constant, minus E g by eta k by e into 1 by T. So, we plot logarithm of I reverse T minus 1.5 log T against 1 by T, where temperature T is in Kelvin. This will be a straight line with a negative slope minus gamma, which is minus E g by eta into k by e. Eta E g is the band gap in electron volts. So, we can find E g from the relation E g is gamma into eta into k by e. We have found eta, we know k by e, we have found gamma, we can find E g. The experimental setup has already been shown to you. There is an aluminum block in which there is a hole, and in this hole we have a copper coil enamel coated of 42 gauge wire. This has a resistance of about 25 ohms. In another hole we mount a platinum 100 resistance thermometer. On one face we fix the diode with araldite. The leads are brought to the terminal block. Between 1 and 8 is the platinum 100 thermometer, which is connected to the temperature indicator. Between 2 and 3 is the copper coil, that is connected to a constant current source. This is set in low current mode, that is the two switches are down, and I adjust a current of 5 milliamperes to flow through the coil. The voltage across the coil is read on this multimeter in millivolts. It is 138.5 millivolts. Between 5 and 6 we have a diode. Between 4 and 2 we have 2K at room temperature. Between 7 and 6 we have 470K. I have a box here, and in this box I have a 1.5 volt cell which is connected to a 2K port. So, at the variable point of the 2K port, I can get any voltage between 0 to 1.5 volts. This voltage comes to the pair of terminals T2 if I put this switch down. This voltage is used as the forward voltage for the silicon diode. We can change the forward voltage and we can measure the current. There is a 9 volt battery which is connected through the switch to these two terminals T1. That is used for measuring reverse saturation current of the diode. So, I now take my sample at room temperature. I connect the terminals 4 and 6, 4 to the red terminal T1 and 6 to the black terminal on T2. I use a multimeter which is to measure the forward voltage between 5 and 6, that is the red and the black terminal. So, now the forward voltage is 0.3 volts. Forward voltage is 0.3 volts. If I change this, forward voltage will increase. So, I start with 0.3 volts. There will be a forward current which will flow through 2K. So, I measure with the same multimeter the voltage between 4 and 5. That gives, that is 6.4 millivolts. That will be proportional to the forward current. So, I can set the forward voltage whatever I want, 300 millivolts, 325 millivolts, whatever I want, and I can measure the forward current at this temperature. So, I connect the variable voltage terminals T1 on the box to the terminals 5 and 6, to the terminals 4 and 6 on the terminal block, not 5, that is wrong, terminals 4 and 6 on the terminal block. Terminal 4 should be connected to the positive terminal on the variable voltage box and terminal 6 to the black terminal of the variable voltage box. Note the temperature T on the temperature indicator, convert it to Kelvin. Use a DMM in the 2000 millivolt range to measure the voltages across terminals 5 and 6 and 4 and 5 on the terminal block. Voltage across 5 and 6 is the forward voltage applied to the diode, and voltage across 4 and 5 is the voltage across 2 kilo ohm resistor proportional to the forward current. Adjust the potential on the variable voltage supply to apply a forward voltage between terminals 5 and 6, varying from 300 millivolt to 500 millivolt in steps of 25 millivolt. For each value of the forward voltage, measure the voltage across terminals 4 and 5. So, this is the table, this is the forward voltage, 300 millivolts is 0.3 volts, 2.5 volts, and the corresponding millivolts across the 2K resistor, which is proportional to the forward current. So, I take the natural logarithm of this voltage, logarithm to the base e, and that is in the third column. I plot logarithm of the voltage along the y-axis and the forward voltage along the x-axis. The points lie on a straight line. I find the slope of this curve, that is of this straight line, that is 20.6 per volt. The temperature of measurement when I did this experiment was 30 degrees centigrade, that is 303.1 K. The slope beta of this curve is 20.6. So, we calculate eta from the relation eta is 1 by slope multiplied by K by E, 86.6 microvolt per Kelvin, into capital T, which is 303.1 K, and eta comes out to be 1.83. This is the first part of the experiment you should do at the start before heating the furnace. Then, for the reverse saturation current, I now switch off the variable voltage, I switch on the 9 volt, I remove the connections from 4 and 6. And connect them. 4 must now be connected to terminal 7. Four must be connected to terminal 7. That is, the red wire must be connected to terminal 7 and the black wire must be connected. The black wire must, or the blue wire here must be connected to terminal 5. I put in the plugs to the terminals of the 9 volt supply and switch on. For measuring reverse saturation current of the diode, connect the 9 volt terminals of the voltage source. The red terminal must be connected to terminal 7 on the terminal block and the black terminal to terminal 5 of the terminal block. Now a current will flow through 470 kilo ohms and the silicon diode in the reverse direction. The voltage V across 470 kilo ohms is proportional to the reverse saturation current. So I connect this DMM to the terminals 7 and 6. Between 7 and 6 you have 470K. I connected between the terminals 7 and 6 and measure the voltage. So it shows very small voltage. It shows a voltage of 5.8 millivolts. For TCR of copper, I connect terminals 2 and 3 to the constant current source. In the low current mode, set a current of 5 milliamperes. The voltage across 2 and 3 will be proportional to the resistance of the copper coil, and that is measured on another DMM. Then I close the top with cotton and then connect my power supply, set a voltage of about 8 volts and adjust this voltage so that temperature rises by 1 degree per minute. Then note the reading on DMM1, which is the voltage across copper coil, and DMM2, which is the voltage across 400K connected to the silicon diode. Note these two readings for every 10 degree rise in temperature. So the readings are given in this table. I have taken readings at these temperatures. This is the value of the voltage across the copper coil, and I plot this voltage against the temperature I get a straight line. I find that this straight line has an intercept 137.2 millivolt, slope 0.636 millivolt per centigrade. So, the temperature coefficient of resistance alpha is slope divided by intercept, that is 4.64 10 power minus 3 per degree centigrade. These are the readings taken with for the reverse saturation current. The first column gives the temperature in centigrade, second column gives the temperature in Kelvin. You add 273.1 to the readings in the first column. Third column gives reciprocal of temperature in Kelvin, that is reciprocal of these values are given in the third column. The fourth column gives you the voltage across 470 K measured on the multimeter 2 with 4.9 millivolts and increases to 718 millivolts at 100. You take natural logarithm of the voltage, subtract 1.5 times natural logarithm of the temperature in Kelvin, that is given in the last column. You plot log V minus 1.5 log T along Y and 1 by T along X. You get a straight line with a negative slope minus 7458. So, the slope minus gamma is minus 7458 or gamma is 7458. So, the band gap is the non-ideality factor eta, which we measured earlier, 1.83 into the slope gamma 7458 into K by E, which is 86.6 microvolt per Kelvin. Eg comes out as 1.17 electron volt.